Hello and welcome to lecture 29 of the course Computational Complexity. So in the past two lectures, we have seen the complexity classes for randomized computation. We have seen RP, co-RP and BPP, which correspond to the complexity class, which correspond to Monte Carlo algorithms, those that that run in a fixed some fixed time, but then they could result in errors, meaning yes instances could be reported as no's or vice versa. In this lecture, I want to talk about ZPP, which is a complexity class that pertains to Las Vegas algorithms, where the running time varies, but correctness is assured. Okay. Before getting into ZPP, I want to state one small point, which I think is an important point, but I didn't emphasize this in the previous lectures. The point that I want to make is that we have seen the probabilities, right, throughout. In the case of RP and co-RP and BPP, we have seen these probabilities. So the way to understand these probabilities is that, let's say, consider this, the BPP for instance. The probability is always over the random choices made by the algorithm. Okay, so when I say X is in L implies the probability of acceptance at least 2/3 means X is fixed, and for any fixed X that is in L, the probability of it getting accepted should be at least 2/3, and the probability is taken over the random choices made by the algorithm. So the algorithm may make many random choices, and then it is taken over all the random choices possible for every fixed X that is in L. So any fixed X, there is at least 2/3 probability that it will be accepted, and whenever X is not in L, any fixed X that is not in L, the probability of acceptance is at most 1/3. Okay, so it's not like half the, like one X is there that will never be accepted, not like that, right? For any X that is in the language, the probability is taken over the random choices, or for that matter for any X, whether it is in L or not in L, the probability is taken over the random choices made by the algorithm for any fixed X. Okay, so let us go to ZPP. ZPP stands for zero error probabilistic polynomial. So L is considered to be in ZPP. Okay, if there is a probabilistic polynomial time machine M that can answer yes, no or don't know. Okay, so this is the new thing here, is that we are allowing the machine to say I don't know. Okay, such that the answer is always correct, right? So suppose so you have a machine that is always correct, that runs in polynomial time, can use randomness. But if you want the machine to be always correct, you can always have the machine truthfully say I don't know, right? So this is not interesting. Like what uses a machine that always says I don't know? So to make it interesting, or to make it useful, we limit the probability by which it can say I don't know. For any X, the probability for which it should say I don't know is upper bounded by half. So with probability half, it should give the correct answer. So it cannot say yes and no both for the same input, right? Because it always has to output the correct answer, right? So if X is in the language, it can either say yes or I don't know, and the probability of saying I don't know is at most half. If X is not in the language, it could either say no or I don't know. The probability of saying I don't know is at most half, and it is not allowed to say an incorrect answer, right? This is ZPP. So when I make this definition, right, it doesn't seem like what I just said. The running time seems to be fixed in this definition, right? And there are no errors, but then there is a provision of I don't know. But we will later see in the same lecture, we will see why or how we can change, we can do some repetition, tweaking, etc., so that the machine never says I don't know. Instead, the running time becomes variable. Okay, so you can do a trade-off between allowing I don't know and allowing it to take flexible time. Okay, we will see that later in this lecture. So now let us try to understand the class ZPP. So first thing to note is that ZPP is contained in RP. Okay, why is that? Let's say there is a ZPP machine. Let's say M is a ZPP machine for a language L. Now, to show that ZPP is contained in RP, we should show that any language L is also in ZPP is also in RP. So, we take the language L, we take the ZPP machine for L, let that ZPP machine be M. Now, we will demonstrate an RP machine for L. Okay. Now, we modify the machine. It's a very simple trick. So, in an RP machine is not allowed to say I don't know. It is allowed to say only yes and no. So, what do? Whenever M says I don't know, the RP machine constructed, so the RP machine we call it M prime says reject. So now M prime only says accept or reject, yes or no, right. So whenever X is not in the language, M prime always says reject, because whenever X is not in the language, M prime can say, or M could have said I don't know or reject, but now all the I don't knows have become reject also. So whenever X is not in the language, M prime always says reject. So the probability of accepting such an X is 0, which is what RP wants us to do. Any X that is not in L, probability of acceptance should be equal to 0. Whenever X is in L, whenever X is in L, M, the ZPP machine could do two things. It could accept or it could say I don't know. The probability of saying I don't know is at most half. But then now when we convert it to M prime, all the I don't knows get converted to rejects. So the probability of M accepting, anyway, the probability of M saying I don't know was at least half, at most half. So the probability of M accepting was at least half. So the probability of M prime accepting is also at least half. Right? Whenever M accepts, M prime also accepts. M prime only converts I don't know to reject. So again, this is what RP wants. So M prime, so by observing this, you note that M prime is an RP machine for the language L. So whenever an arbitrary language L is considered, L from ZPP is considered, you can show that L is in RP. You take the machine and whenever it says I don't know, you make it say reject. That's it. Similarly, right, ZPP can be shown to be in co-RP. This I would suggest you to work out as an exercise. This is exactly like the same thing. You just have to change I don't know to accept here. Okay, so you can work out the details here. I do not want to get into the details. It's exactly like what we did here. So ZPP is, we saw that ZPP is in RP. We also saw that ZPP is in co-RP. Again, we didn't see, but I hope because of the extreme symmetry here, you are convinced that ZPP is in co-RP, but in any case you can convince yourself. So consequently, we can say that combining both of the things, we can say that ZPP is a subset of RP and co-RP. So it is a subset of the intersection. Right. Now what is true is that it is equal to the intersection. ZPP is equal to RP intersection co-RP. Right. Let's see why. So we have already seen that it is in RP, we have already seen that it is in co-RP. So if it's in both, it's in the intersection. Now all that remains to be shown is the other direction inclusion. We have to show that RP intersection co-RP is contained in ZPP. We have to show that RP intersection co-RP is contained in ZPP. So how do we do that? We take an arbitrary language in RP intersection co-RP and then show that this language is in ZPP. So let us consider an arbitrary language, right? Let us consider an arbitrary language L in RP intersection co-RP. So it is in RP intersection co-RP, which means that it is an RP as well as it's in co-RP, which means it has an RP machine as well as a co-RP machine that recognizes it. So let M1 be the RP machine for L and let M2 be the co-RP machine for L. Okay. So now again, all I am doing is just writing down what we know so far, right? So many steps you will see are standard. To show that something is a subset of the another thing, you just take an arbitrary member of the first set and then show that this arbitrary member belongs to the second set. To show that two sets are equal, you show A contained in B and B contained in A, right? And this is all that I am using here. And once I took an arbitrary member of ZPP, right? We had to show that RP intersection co-RP is contained in ZPP. So we took an arbitrary member of RP intersection co-RP, and then what does it mean? It is an RP, so it has an RP decider. It's in co-RP, so it's a co-RP decider. So now let us write down what it means. So M1 is an RP decider, and M2 is a co-RP decider. Suppose X is in the language, then the RP decider accepts with probability at least half. Right? And the co-RP decider accepts with probability 1. Right? This is what it does. If X is not in the language, RP decider accepts with probability equal to 0. And co-RP decider accepts with probability at most half. Right? So I am just writing down the definition of M1 and M2 based on what we saw for the definitions of RP and co-RP. Okay. So what is to be noted here? M1 is a RP decider. There is only false negative, and it accepts. There is no false positive. So when M1 accepts, X is in the language. When M2 rejects, X is certainly not in the language. M2 has only false positives. There is no false negatives. So whenever M2 rejects, we know for sure that X is not in the language. Similarly, whenever M1 accepts, we know for sure that X is in the language, right? So let's try to understand how things are. Maybe again drawing a small grid picture. So M1 accept. So I'll write down what are the possibilities here. M1 accept, M1 reject, M2 accept, and M2 reject. So can M1 and M2 both accept? Yes, they can both accept. And when M1 and M2 both accept, we know that M1 accepts only when X is in the language, right? So when M1 is accepting, we know for sure that X is in the language. Right? Even when M2 is rejecting, we know that X is in the language. Sorry, this cannot happen because when M1 accepts, when M2, so this cannot happen. Sorry. M2 and M1 accepts, X is certainly in the language, so M2 cannot reject. So this cannot happen. Suppose suppose M2 rejects, we certainly know that X is not in the language. Right? So M1 also may reject. And what can possibly happen is that M1 rejects and M2 accepts. This can happen. Right? So one of the machines rejects and the other machine accepts. Right? This certainly can happen. And then what do we do? Right? So this is a situation that can happen. So what we will do here, so the problem here is to show that, so one direction is already known, ZPP is contained in RP intersection co-RP. We are showing that RP intersection co-RP is contained in ZPP. So using the RP and co-RP decider, we will build a ZPP decider. Okay. So we need to build a ZPP decider. So So now the ZPP decider always has to be correct, but it has an extra weapon. It can say I don't know, right? So whenever M1 accepts this situation, the top left quadrant, it can say x1 is in the language, x is in the language. This situation does not arise, top right does not arise, right? It cannot happen. Whenever M2 rejects it, one can say that x is not in the language. So the only situation is this one, when M1 rejects and M2 accepts, which is possible because M1 allows false negative and M2 allows false positive. So it could be that x is in the language and M1 is reporting a false negative, or x is not in the language and M2 is reporting a false positive. So it could be either case. But then a ZPP machine, which is what we are trying to construct, can always say I don't know. So this is what we do here. So let me just formally describe all that. The M prime is the machine, ZPP machine that we are going to construct. This is the ZPP machine, or let me say target ZPP machine. So to build M prime, we run both M1 and M2 on X. We accept if M1 accepts and we reject if M2 rejects. So as I said before, it cannot happen that M1 accepts and M2 rejects. Right? And the confusing situation arises when M1 rejects and M2 accepts. In that case, we say I don't know. We say I don't know. So now to verify that this is an ZPP machine, we need to do two things. One is that the probability of I don't know is bounded to at most half on any input, and two, otherwise all the answers are always correct. So the second part is already done. We know that M1 accepts only when X is in L. We know that M2 rejects only when X is not in L. So we know for sure that the accept reject responses are correct, and don't know responses are always correct, right? So you can say I don't know anytime, right, and always be correct, unless you know the answer, but then machines don't do that, right? So the only thing that is left to be verified is that the probability of I don't know is at most half. So let us see. Suppose X is in the language. How can we say I don't know? If X is in the language, then we say I don't know because M1 rejected. What is the probability that M1 rejected? Well, the probability that M1 accepts when X is in the language is at least half. So the probability that M1 rejects is less than or equal to half. So the probability that M1 does not accept when X is in L is at most half. And this is when M prime saying I don't know. So the probability that M prime saying I don't know is at most half. M prime says I don't know only when M1 answers incorrectly, and that happens with probability at most half. Similarly, when X is not in L, why does M prime say I don't know? This is happening because M2 is accepting. And what is the probability that M2 accepts when X is not in L? The probability that M2 is accepting when X is not in L is over here. It is at most half. And that is when we say M prime says I don't know. So the probability of saying M prime saying I don't know is at most half. So therefore, we can conclude that the machine M prime is a ZPP machine. So whenever L is in RP and co-RP, it is in ZPP. Therefore, we have shown that ZPP is equal to the class RP and co-RP. So maybe it is an important-ish result. I'll put it in a red box. Sorry. So, okay. Now finally, one more point about ZPP. This is what I promised at the beginning. So so far we know ZPP as a type of machine that runs in a fixed time but allows to say I don't know. But I motivated ZPP by saying that it corresponds to Las Vegas algorithms, one where the running time is variable but correctness is guaranteed. Now let us see how this definition corresponds to that, right? So this is the next theorem. ZPP is a class of languages for which there is a probabilistic machine that runs in expected polynomial time. Okay, so it's a probabilistic machine that runs in expected time OTN, where Tn is a polynomial. So expected polynomial time, which means the running time can vary. The expectation of running time is polynomial, such that whenever m halts, it correctly outputs the answer. It may run for a long time, that's okay, but when it halts, we get the correct answer. Okay, and the expected running time should be polynomial. So in some particular input, it may take a long time, or in some cases, maybe just that all the randomness is not working out to our favor, but it may take some time. But the expected running time is polynomial. Again, the expectation is calculated when the probability is taken over the random choices and not the choices of the random bits and not the choices of the input. Okay, for any input, this expectation should hold. So let us see why this is the case. So there are two things here. One is that we have already made a definition for ZPP, that ZPP is a class of languages that have a probabilistic polynomial time machine that says yes, no, and I don't know, but always answers correctly whenever it gives an answer. Right. So now from that definition, we have to show that definition implies this definition, or this definition, this characterization, and this characterization implies that characterization. Okay, so I'll give a brief proof sketch, because again the proof details are simple. I'll give a brief proof sketch. Suppose L is in ZPP, okay, which means it has, as per the first definition, it has a probabilistic polynomial time Turing machine that says yes, no, and I don't know, and probability of I don't know is at most half. What we can do is to repeat, let's say, so now how do we build a machine that of this nature that I said here, that the theorem statement says? Okay, so we need a machine that does not say I don't know, right, but can take variable time. So the simple way is, the simple way is it's taking a bit slow. The simple way is to run the ZPP machine. So maybe let's say M is a ZPP machine. Okay, so M prime is what we will try to do. M prime is a machine that will fit the characterization in this theorem statement. So M prime is just this: run M if M outputs don't know, then repeat, and repeat till we get a accept, reject, or yes, no. Right, so we repeat it till we get a accept or a reject. Let's see why this works. What is the expected running time of M prime? So certainly it will be repeated till it is accepting or rejecting, and we know that M is a ZPP machine, so M will always output the correct answer. So that way it's all fine. The only thing that remains to be verified here is that running time is an expected polynomial time. So what is the running time of M prime, or expected running time of M prime? Right. So how many times will we have to repeat this? So the probability of, so whenever M says don't know, it has to be repeated. So how many times should it be repeated so that we get an accept or reject? Right. So does it remind you of some probability distribution that you know? So if you have a die, 6-sided die, not normal 6-sided die, how many, like, what is the probability of getting a 6? It is 1/6. Suppose you keep rolling till you get a 6. What is the expected number of rolls to get a 6? This corresponds to a geometric probability distribution, right? And then expected number of trials is 1 divided by the probability of success. So in the case of die, it is 6 times, right? Here the probability of getting a correct answer is half, or at least half, right? So it is at least half. So the probability of saying don't know is at most half, right? So expected running time is at most 1 divided by the probability of getting a because the probability of getting a accept reject is at least half. So that's why we have to write at most multiplied by running time of M. And we know running time of M is polynomial time, because that's how we define ZPP. The running time is polynomial. So this is equal to, and this quantity is nothing but 2. 2 into time taken for M. So it's a polynomial time machine. So the expected running time is polynomial, or at most polynomial, so which is fine. So whenever L is in ZPP, we construct, we get a machine as described in this theorem statement simply by running M again and again and again till it outputs a accept reject answer. Whenever it says I don't know, you repeat. And we know for sure that whenever it says accept or reject, it is a correct answer. Now the other direction. Suppose there is a machine like this which runs in expected polynomial time, right? So the running time can vary, but at the end, whenever it halts, it will give the correct answer. Now how do we go to a machine which has a fixed running time? Right? How do we go to a machine that has a fixed running time? That's also not very difficult. Suppose there is a machine as we said in the theorem statement, okay, which means it has running time, that is expected running time is something. Now the idea is to run the machine for a certain time, okay. So certain time, what works is, so let us say the expected running time is maybe this works, I think 2 times the expected time, right? So this works, I think. And the thing is, it may not conclude, right? Because the statement, the theorem statement, we say it may run, the bound is known only for the expected running time. A specific input may take long time depending on the random choices made. But we know that the expectation is fixed. So we can, and we can allow it to run till certain time. If it does not complete its execution till that certain time, okay, if it does not complete its execution till that certain time, we just stop the execution and say I don't know. because now in the ZPP model we cannot have the flexibility of running forever, but we do have the flexibility of saying I don't know. So if it has not completed the execution, you say I don't know, right? So you run a machine M. So maybe I'll just write in a bit more detail. Okay, write in a bit more detail. Say M is the machine as in the theorem statement. So the ZPP machine will be M prime, sorry. Or I'll call M prime the machine in the theorem statement, just because earlier also M prime corresponded to the theorem statement, and ZPP machine will be M. Okay, so what is M? Start M prime, run till time, expected time of M prime, sorry, run till time 2 multiplied by expected time of M prime, 2 multiplied by this, okay. If M prime completes, output the same as M prime. If M prime does not complete, then we are stopping it. Does not complete, output don't know. So this works because of what we have here called Markov's inequality. When a random variable is non-negative, we have the probability that it exceeds a certain quantity is at most expectation of the random variable divided by A. So where A is the quantity that we are doing this. In other words, sorry. So when the probability that it is more than 2 times the expectation is at most half. So when you apply this for x equal to the running time, for the expected the running time of M prime, it works out to be the probability that you end up saying don't know is a probability that you exceed the running time of the expectation of twice the expectation. So the probability that you exceed x exceeds twice its expectation is at most half, and that is the probability by which you will say I don't know. And correctness, it runs in polynomial time because you are stopping the machine at a certain time. So you know that it runs at a certain time and the answers are always correct. As an exercise, you could I gave most of the details, but if you want to convince yourself, you can work out the rest of the details. And with that, I think I will conclude this lecture and I will quickly summarize. We stated the model ZPP, or the complexity class ZPP, for which we gave two definitions. One is the Las Vegas algorithms, where which we saw at the end, where the machine will always be correct, but the running time is variable, and The second definition, which we saw first, was that the running time is fixed, but the machine can do three things: yes, no, or do not know, don't know. So it has a don't know option, but the probability by which it can output the don't know is limited, right? And the thing that we observed is that ZPP is equal to the intersection of RP and co-RP. And the interrelation between all these are very interesting. Like you see how we proved ZPP is equal to RP intersection co-RP, and also the proof that both the definitions, ZPP is the model with yes, no, and don't know, and the model where the running time is variable, but the correctness is guaranteed with only yes and no. And both of these make use of interesting probability and some simple but interesting tricks. We'll conclude with a summary of week 5. We first saw the Baker-Gill-Solovay theorem, which said that techniques that relativize, in particular diagonalization, cannot be used to resolve the P versus NP question. Right? So this was done by demonstrating two oracles A and B such that P to the A is equal to NP to the A and P to the B is not equal to NP to the B. So because of these two oracles, we cannot use techniques that relativize to show or to resolve P versus NP. After the proof of the Baker-Gill-Solovay theorem, we went to the randomized complexity classes, starting with the motivation. Then we first saw the classes RP, co-RP and BPP, which were classes that correspond to Monte Carlo algorithms. We saw how to do boosting for each of these classes, how we could repeat the algorithm and improve the errors. We saw how these complexity classes relate to each other. We also saw ZPP, complexity class pertaining to Las Vegas algorithms. We also saw how this class relates to the other classes that I have already mentioned. We saw at least two characterizations of ZPP and how the equivalence between them. We also saw the proof that ZPP is equal to RP intersection co-RP. Right? And with that, I think we concluded this week. And next week we will start off where we are from this point. We will see some more randomized complexity classes, how they relate to some other things that we have already seen, and take it forward from there.